Peace. Huh. Peace. Power. Mad liberator, death operator, rock the data, amazing flavor. Yo, the way I feel, sometimes it's too hard to sit still. Things are so passionate, times are so real. Sometimes I try to chill, mellow down, blow a smoke. A smile on my face, but it's really no joke. You feel it in the street, the people breathe without hope. They going through the motion, they dimming down the focus. The focus get cleared and the light turns sharp and the eyes grow teary, the mind grow weary. I speak it so clearly, sometimes y'all don't hear me. I push it past the base, no nations got to feel me. I feel it in my bones, black, I'm so wide awake that I'm hardly ever sleep. My flow forever deep in its volumes of scriptures when I breathe on a beat. My presence speak volumes before I say a word. I'm everywhere, penthouse, pavement, the curb, cradle to the grave, so cathedral of a shell. Universal ghetto life, holla black, you know it well. Quiet storm, vital form, pen push the bright across. Mind is a vital force, hollow right across. Soul is the lion's roar, voice is the siren. I swing round, ring out, and bring down the tyrant. Chop a small axe and knock a giant lopsided. The world is so dangerous, there's no need for frightened. The suckers trying to hide like the struggle won't find them. Then the sun busts through the cloud to clearly remind them this everywhere. Penthouse, pavement, the curb, cradle to the grave, talk cathedral of a shell. Universal ghetto life, holla black, you know it well what it is. You know, they know what it is. We know, y'all know what it is. Ecstatic, there it is. Huh, what it is. You know, we know what it is. They know, y'all know what it is. You know, here it is. What it is. You know, we know what it is. They know, y'all know what it is. You know, here it is. Peace, power. Fantastic. Original. And always on time. And rocking your mind. It's like
sit and come relax, riddle of the Mac, it's the patch. I'm a soldier in the middle of Iraq. What say about noonish, coming out the whip and looking at me curious, a young Iraqi kid carrying laundry. What's wrong, G? Hungry?
No, give me my oil, get out my country.
And in Arabian, barking other stuff till his moms come grab him and they walk off in a rush. Distrust, feeling like I was pissed up on wound. I'm like, surely hope that we can fix our differences soon. Buying apples, hun breaking on.
Brute, you take everything, why not just take the damn fruit blockbuster?
I don't understand it. On another planet? 15 months of this stuff, how I'm gonna manage? And increasing this sentiment, gentlemen getting down on their Middle Eastern instruments. Realize trapping this crap. Walk over, kicked one of my fabulous raps. Arab jaw drop, they well wish, they glad rap. Now the kid considered like an Elvis of Baghdad.
هذه ما تربحش وهذه ما تربحش، هذه ما تربحش، هذه تربح، هذه تربح، لازم، هذه ما تربحش وهذه ما تربحش، دايما على لازم.
What it is.
قاعد عندنا فلوس واحد يضحك واحد يبكي.
تو اللي بعتوك.
إيه أنا اللي بعتوني. ها.
What it is. You know, they know what it is. We know, y'all know what it is. Ecstatic, there it is. Huh, what it is. You know, we know what it is. They know, y'all know what it is. You know, here it is. What it is. You know, we know what it is. They know, y'all know what it is. You know, here it is. Keep on rocking you.
All right, so to continue where we left off last time, we were looking at binary search trees, which are binary trees that store key data, and for our purposes, that'll be an integer, in a manner such that if you've got a key value here at a node, every key value in its left subtree is less than that key value. And then every key value in the right subtree is greater than that key value. So we're not going to allow duplicates. That's just a technical issue that we can get by. But ultimately, what this does is it allows you to search efficiently, or at least when proportional to the depth of your tree. For example, if you want to search for 45, all you have to do is start at the root, see that 45 is less than 50, the root value, and so you go over here to 40, and then you go over here to 45, and you found what you're looking for. Sometimes you'll get lucky and you'll find something shallow in the tree up here. Sometimes you won't get so lucky and you're searching for something deep in the tree or something that doesn't exist. In which case, you know, it's you have to go the entire depth of the tree here, depth, right? And so what we did is we've developed that algorithm and we went through a couple of examples. Here's the pseudocode to do, oops, sorry, back, there we go. Here's the pseudocode to do it. We're given a binary search tree T and a key K, and what we want to do is we want to find an element X such that X matches our key. Otherwise, we'll output phi because there's no such element. We do have to take into account that, you know, not everything exists here. If I'm searching for 76, for example, I would get down here eventually here and find that it doesn't exist. And so I do need to output null, or phi in this case, if no such element exists. We will start at the root element, right? And we don't know how deep we're going to get because, again, sometimes we get lucky, sometimes we get unlucky, sometimes it's an unsuccessful search. So I'm going to go into a while loop here. While I've not fallen off of this tree, while I keep going down and I've not fallen off the edge of this tree, I'm going to update current. First of all, if the current is, its key value is what I'm searching for here, then I'm done and I output whatever data is right there. Otherwise, if the key value that I'm searching for is less than the current's key value, right, that means I'm looking at this and I'm searching for 44. I go left. And the way that I do that is by simply updating the current to be the current's left child. Likewise, if the key value is greater than the current's key, then I go right by updating the current's right. Now again, this is, strictly speaking, this is not necessary here because it's either equal, less than, or the only other possibility is it's greater than. But once I get out of this while loop here, then I'm out of options and I've fallen off the edge of this tree, 76 for example. It does not exist. Therefore, I output phi. Right? Eventually, I'll fall off the edge of the tree or I'll find what I'm looking for. Okay? Now what I want to do is I want to start developing this. The first step is that we need a binary search tree. All right, so what I'm going to do is I'm going to create a new class called binary search tree. Search tree. There we go. And I'm going to immediately parameterize it because I want this to be a binary search tree that can hold any type T. Strings, doubles, sales, whatever. Right? Now you might think, well, wait a second. We've already done a whole bunch of work over here with this binary tree. A binary search tree just has some additional more specific properties. For example, that everything over here is less than the key value and everything over here is greater than the key value. So I might be tempted here to say that this extends binary search, right? Or binary tree. There we go. And I end up inheriting everything that it means to be a binary tree. Right? For example, I inherit a pre-order traversal. Does that make much sense, though? What does a pre-order traversal get me in a binary search tree? Right, here, let's go over here. What would a pre-order traversal be? It'd end up being, say, it'd end up being 50, 40, 20, 10, 2. Maybe that seems promising. It's in descending order. But then I get over here, and what do? 15, 12? No, it's just some other order. It doesn't get me that much. What does get me a lot, though, is an in-order traversal. So what does the in-order traversal do? It does everything in the left subtree, then it does the root, then it does everything in the right subtree. 1, 2, 3. Can you see the pattern that's immediately going to merge from this thing? Let's go ahead and go all the way down here. I do 2. I do its left child, which doesn't exist. Then I do 2. Then I do its right child, which doesn't exist. 2. What's going to come next? Well, I'm done with this left subtree off of 10, so I do 10. I process 10. And then what do I do next? The right subtree here. But I don't do the root node immediately. What I do is its left subtree, then the root node, then its right subtree, which does not exist, which gives me 12 and 15. Tell me what the rest of the pattern is. 20, 24, 28, right? Et cetera, et cetera, et cetera. Why do you think it's called in-order traversal? Because when you perform it on a binary search tree with this property that everything over here is less and everything over here is greater, right? Less than k and greater than k, what do you get? You get an in-order value here, right? So an in-order traversal does buy me something, right? If I were to do, where is it? There. In-order recursive and print them out, I would end up having having printed it in ascending order. But does pre-order traversal get me anything? Does BFS traversal get me anything? No. In fact, I never even implemented this insert method here. I waited to do that because I don't know how to do that with just a regular binary tree, right? So I'm not going to extend binary tree because it's not. I don't want to inherit all that stuff. Not all that stuff makes sense, right? I could do it just another way, though. I could prefer composition over inheritance. Do you remember when we did that? And do public tree, binary tree, not public, sorry, private binary tree T underlying tree. Right? We've done this now several times, right? We've done this when we did, in fact, you did this in your lab last week, I think, right? To implement a stack, you used a linked list or a deck or something like that, right? Internal. We didn't extend a linked list because it was a restricted access data structure. We didn't want to inherit all that stuff. We didn't want to lock ourselves into an inheritance hierarchy that didn't make sense. Go back to the beginning of the semester when we started looking at inheritance. We also didn't want to do that with our people. We have directors and we have authors. They're both people, yes, but some people are both a director and an author. We didn't want to lock ourselves into that rigid hierarchy. Right? So this is one solution. Instead of inheritance, we prefer composition. But for now, what I want to do is I just want to start from scratch. What I will have is a tree node T. Right? Okay? And this is going to be a root. Right? I'm going to keep track of the root just like I did over here in the binary tree. Okay? So now I can go ahead and worry about how to get things in there, how to search for stuff, how to, the basic CRUD, create, retrieve, update, and destroy. Let's go ahead and create a public method here for binary search tree, right? For constructor though. This .root is going to end up being null, right? And also, if you're going to keep track of other things like we did with our list data structures, maybe we want to keep track of the size. And so I will initialize this .size to be 0. Should be an integer, sorry. There we go. All right, just like the binary tree, I'm eventually going to want to get stuff in there. Right? So I'm going to go ahead and copy that over. Right? We'll wait on that though. Right? That's the second operation. We've only so far looked at the search operation. You start at the root and you traverse left or right until you go past the leaf, and the complexity here is order D. However, there's no guarantee on that. There's no guarantee that it's going to be logarithmic. Like we saw on Friday, there could degenerate into just a regular old linked list, which is going to still be order n operations. Right? What I want to do, though, is I want to codify this pseudocode here into Java code. Right? We can do this a couple of ways. Right? Public find element. Right? And what I'll do is I'll give it an element of that type. Right? What I could do is I could return a tree node that contains that element. Right? That's one way of doing it. Right? So returns a tree node containing an element that matches the given key. In fact, let me go ahead and rename that. That's going to be a key element there. Right? Is it a good idea to return a tree node? Let me come over here to my demo. And instead of a binary tree, let's go ahead and go with a binary search tree. Right? And eventually, a new, I do have one here prepared, but we'll get there eventually. A new binary search tree on the same type here, strings. Instead of strings, though, let's go ahead and do integers. Right? Okay. Now, demo.find find element. Oops, find element. And I do need a key here, so what I'll do is I'll go, I want to find 10 in there, right? And what's that going to return? Well, that's going to return a tree node. So let's go ahead and capture that value over here. Tree node t, or integer, right? Node is equal to. Does that sound like does that look like a sound design, right? Ultimately, yeah, I'm calling this a binary search tree, but I'm going to go ahead and give you the tree node so that you can, okay, well, thanks for that node. Now I need to actually get the value out of that. Integer x is equal to node.get element, right? In other words, I have to rip open that node anyway to pull out the element. Does it seem like a good idea that I should be returning a tree node? That's the internal representation of the tree, right? We didn't return a node when we did a linked list, right? Why did we not do that? Because that was a leaky abstraction. We are leaking information out to the outside world that this thing is built on tree nodes. And tree nodes have an element, a left child, a right child, and a parent, right? We don't want to do that. We want you to be able to use this collection and just use it, right? I don't want to get this tree node and then have to rip it open or anything like that. In fact, I don't want to know anything about tree nodes at all. All I know about is this thing that holds integers. I will worry about those integers. Integer x is equal to, right? So that's what it should look like. And instead of returning a tree node, I will return t, an element that matches that element. Returns on element that matches the given key. Let's go ahead and document it at code null if no such element, right? Right? Because it is going to be an unsuccessful search from time to time. All right, let's translate this code here, right? We're given a binary search tree because we're inside that class. We're given a key element k here that I called key. And what we want to do is we want to output phi. Well, our placeholder for that in Java is going to be null. Otherwise, we output the actual element here. I'm going to set this up by keeping track of a current element. Tree node t current, right, is equal to, where do I start? This dot root. There, this dot root, or the tree's root. Now you do have to be careful here. Consider to do. What happens if there is no root element? In other words, it's an empty tree. Right? So I'm going to put that as a to-do here, and we're going to consider the code that I'm about to write. Otherwise, I'm going to go into a while loop here, while your current node is not null, while you've not fallen off the edge of the tree. Right? While current is not equal to null. Then what I'll do is I'll have a series of if-else-if statements. If the key value in the current node is equal to the element that I'm looking for, then I'll return it, right? So if the key value is equal to current.getKey, or .getElement, excuse me. There we go. All right. Equals, maybe. Return current.getElement. There we go. Else if the key value, and how did I phrase this before? The key value that we're passed in is less than the current's key. Key value is less than current.getElement. Right? Then I need to traverse left. Okay? And to do that, I will say current is equal to current.getLeftChild. I don't have to check if it exists here, because if it doesn't exist, current will end up being null and we'll end up breaking out of this while loop. And once we're out of that while loop, I'll return null. The only other thing I have to check here is else if the current.getElement is less than the key element, then I will traverse right. So current is equal to current.getRightChild. Now there's a conundrum. It's not compiling. The key and the element are both of type T, right? But I can only use strictly less than or strictly greater than if I switch these around. I can only use those for numbers because that's what's built into the language. In fact, what is this even doing up here? Equals. We're still seeing this mistake on some things, right? For example, if I have a string s is equal to hello, right? And then string t is equal to hello, right? Is the following correct? If Actually, I'll even get rid of that second one. If s is equal to hello. Right? Those coming from a Python background will say, yeah, that's perfectly fine to do in Python. In fact, in a lot of programming languages, it's perfectly fine to do that, right? And mostly in dynamically typed languages, Python, PHP, JavaScript, stuff like that, right? But it ain't okay over here in Java. What is this? This equality is testing what? Yeah. Where something is stored, right? It's saying, is this the same thing in memory? Is this memory address over here the same as this memory address over here? Right? Now in Python, it would actually say, all right, is the content stored at that memory location equal to the content over here on the right-hand side, right? But that's not what it means in Java. Equals equals is simply just making a memory address comparison, just like C, C++, and a bunch of other statically typed languages. This is not how we do this, all right? And even if it were how we do it, it's not how, we can't do it like this. So one way that we could do this is by asking dot equals, right? Because that's how you do it properly with, say, strings. Equal, you gotta spell it correct though. There we go. Dot equals, all right? That assumes, however, that somebody has gone in and generated the equals and the hash code method properly, okay? So I don't even want that. And besides, that doesn't solve my problem down here, right? Strictly less than. So what is another thing that I could have that would compare elements of type T, right? I want to compare T sub x versus T sub y, right? If I have these two variables here, x and y, I need to compare them. Does x come before y? Or does y come before x? Right? Or are they equal conceptually? Right? What is that thing that will tell me that thing? What happens there? That they go like this, or they go like this, or they're equal. What is that thing? A comparator. Right? Unfortunately, I don't see a comparator here at all. Remember, a comparator takes two elements. It has this compare method that takes two elements and returns something negative, positive, or zero, depending on the relative ordering of those. I don't see a comparator here, though. So that probably needs to be part of my state. Right? Let's go ahead and add one. Private. In fact, I'll make it final here. Comparator for elements of type T, and I'll just call it CMP here. CMP, short for the comparator. Let's go ahead and bring this in, import this. Now I made it final so that I would be forced to take this at instantiation. Because again, is this a binary search tree for doubles? Is it a binary search tree for strings? Is it a binary search tree for sales or people or whatever, right? It's all of those things, but you have to tell me how to order those things. Right? And when you have to tell me when you create me, I'm the binary search tree here. And I'll call it CMP. This.cmp is equal to CMP. All right, there. Now that we've got this comparator, these questions can be changed, or these questions can be asked now. CMP.compare2. Right? Compare, say, the key element here with the current element's get element. In fact, what I'm going to do is I'm going to save that off into, I'm going to save that off into a variable. Int result is equal to that. Right? Why? Because I don't want to call it multiple times. I'm going to have to call it once to see, are they equal? Or are they out of order and I need to traverse left or right? Right? Are they in order? And so I'm just going to put that into the result here. And the result is either 0. If the result is 0, then that means that you've found what you're looking for. Return the element. Otherwise, if the result is less than 0, that means that they are in order. And because I said key and current value, that means that the key is less. Right? Here, traverse less. Why? Because the key is less than the current element. The only other possibility here is that the result here is greater than 0, right? In which case, I traverse right. That is, the key is greater than the current. Okay? Now, question here, do I really need to ask if strictly greater than 0? It's either 0, strictly less than, or strictly greater than, so I can actually get rid of that entirely. Okay? Awesome. Right? Now, it would be wonderful if I could test this, but I do not have a way of getting stuff in here yet. Once I have a way of getting stuff in there, then I can test it. Right? So I actually need to implement both of these functions before I can do this. For that, we're going to have to discuss how we actually get stuff into the tree. So there's the search. What about the insert? Right? Insert. Right? Okay. You again start at the root. Right? You do a basic search. Right? If the element exists, do blank, whatever that means. Right? In other words, we do not allow duplicates. Right? So let's take care of this corner case first of all. All right, so suppose that I wanted to insert, say, 45. Insert 45. I'm going to do a search. 50. 45 is less, so I come down over here. 40. It's greater. Oh, I found what I'm looking for. What should I do? Should I insert another 45 if I'm not going to allow duplicates? No, it's already there. Should I kick it out and then replace it with itself? That doesn't seem satisfying either. All right, so what happens? Right. What are my options? Option 1, throw away fit, right? An exception. So we can throw a fit and throw it back at you, say, nope, no duplicates allowed. We're not going to allow you to do that. Right? Option B. What's another option? Nope. Do you remember what that stands for? Don't do anything. No operation. Right? No operation means don't do anything. Right? Just return. Okay. Option C. Nope, but also inform the calling function. Right? That nothing happened. Okay. So, for example, over here, right? Instead of a void, what I could do is I could have a Boolean. Now let's document what that Boolean means. Inserts the given element into this binary search tree. If the element is a duplicate, then false code, false is returned. Right? Actually, let's go ahead and rephrase this. Returning code, @code, true if the insertion was successful, and then false is returned if it was a duplicate value. Right? In other words, we don't insert it, but we tell you that that we did insert it. All right. If we do insert it, then we tell you that it was successful and that it actually had a change on the underlying tree. Otherwise, if the insertion was unsuccessful because it was a duplicate, we'll return false. So option B seems like a really good option, but option C seems even better because we give even more information. Option A would have the same effect. We'll just throw it back at you. But then that means that the calling function is forced to surround everything with a try-catch. And now, having worked with JDBC for the last 3 weeks or so, do you like checked exceptions? I don't. I hate them. Right? Everybody else hates them because nobody else ever adopted them. Right? It was a mistake that was made back in Java 2 or whatever, whenever they introduced it. Right? But in any case, I like option C a whole lot better than option A. Right? I like option C way better than option B because it gives more information. Okay? All right, so that's going to be our how we're going to handle duplicates. Right? But we do a basic search. If no such element is found, then you end up at a leaf leaf node, right? You end up where the element should have been. if it existed. Right? So all we need to do is insert it as a leaf node. Insert as a new leaf node, taking care of the left or right child of the parent and the parent reference. Right? So that's how we're going to do it. Let's come over here and think about the other one that I was looking at, 76. So we'll insert 76, excuse me. There we go, 76. Okay? The way that we're going to do that is by a basic search. So we're going to go ahead and 50, 60, 90, go down here to 80, go down here to 75, and this is where it ends up being if it were to be inserted. Right? So this is where we're going to hang it off of. We need to create a new right child of 75, insert that one element, 76, and then take care of the references. But the right child of 75 will end up being this new node, and the parent of 76 will end up being 75. Right? Let's just look ahead here to the analysis. Right? How many comparisons am I going to have to make to do this? Right? So the complexity is that of the search. Right? All you have to do is search for it, and once you've found where it is not or where it should be, right, then you're done. In other words, it's going to be the same. Order D. Why? Because creating this node and then changing two references, that looks really familiar. Right? Creating a new node and making sure that one node points to it and that it points back to that node. That's the same operation that we did with the linked list. Right? We just didn't do a doubly linked list. We're going back and forth like this. All right? Okay, so let's come over here and actually do it. All right, to do, finish this. All right? I'm going to do the same thing over here, find element. All right? And I'm going to cut and paste this code and then modify it. That feels really icky, and it should be for a reason. Do you cut and paste code like this? No. I should probably look for a way, after I've done this and make sure that it works, I should look for a way to unify this code right here and this code right here so that that there's one search for something, node or something. Right? For now, though, let's go ahead and do this. To do what happens if there's no root. Oh, we forgot my to-do over here. What happens if there's no root element? I forgot on the search find element. So if there's no root element, then what happens to current? It becomes null. And we end up returning null. It seems like that was a perfectly good thing to do. Get rid of that to do. Right? All right, so let's finish this up. I'll start at the root. While I've not found the thing that I'm looking for, right? Oh, the key value here. Not the key value, but the element. There we go. And I'm not going to return here. Instead, I've found what I'm looking for. So if this were the duplicate element, right? What should I return here? Not that thing, but what did we say that we were going to return? False. Right? We're going to return false if it's a duplicate value. Right? Otherwise, we go down here, and eventually we fall out of this. Right? So at this point, current is, I don't know. What is current at this point? Well, let's go over here. I'm searching for 76. That's not it, it's greater. That's not it, it's greater. That's not it, it's less. Less, and here's my current node. So if I did it this way, cur, I've already fallen off the tree. Is there a way to get back up the tree if I've already fallen off? No, I don't see a way of doing it. So let's go back and keep track of two pieces of information. I want the current, and I'll know that I've fallen off the tree here if current becomes null. But I also want the previous. Why do I want the previous? Because I eventually want to have its right child, or if it's left child, take on a new node value over here. So let's come back over here and set ourselves up for that. There's the current, and here's the previous. Right? I don't care what I initialize previous to. Right? There we go. Null is fine. Right? What I do want to be careful of here is before I go to jump from the current to its left child or its right child, I want to make sure that I preserve previous. to be current. Right? There we go. And there. Right? Now, do I care what current is? No, because current is null. Previous is the parent of the new node, ... All right? I have a situation that looks like this. Right? In fact, let's go ahead and draw it more generally here. Here's previous. Right? Now what I want to do is I want to create a new node. New node. And I want to either make it look like this, where I go down from, you know, as a right child, or maybe I want to do it as a left child. In any case, I want to create that new node. So tree node T new child, right, is equal to new tree node containing the element that I was given way up here, right, this element right here. Okay. I've created that new child node. The new child dot parent, set parent, is going to be the previous. Right? That takes care of this. Right? I'm going to be referring back to my parent up here. But now, which one of these situations happens? Should I be a left child or should I be a right child? Right? So, should new child be a left or right child? Question mark. Right? That's where my comparator comes in. I will compare the element to the previous element. Right? Int result is equal to compare the element that I'm given and the previous dot get element. Right? All right. So if the element is less, right? If result is less than 0, then I need to make the element is less than the parent, right? And so I need to go make it a left child. Right? Else if result is greater than 0, then the element is greater than the parent. Make it a right child. Right? How do I do that? I just simply say previous dot set left to be the new child. Otherwise, I say previous dot set right child to be the new child. Right? What about this? Do I need to consider an else here? If it's not strictly greater than 0, if it's not strictly less than 0, then that means that result would be 0. Right? Now, what would that mean? That would mean that the new child is equal to the previous, to its parent. We already took care of that, didn't we? If that's ever the case, then we return false. So no, I don't need to take care of that. Return true. Okay. There. Ugh. I don't know if this is correct or not. In fact, are there some corner cases here that we didn't consider? Certainly, if you gave me a null value, we're going to reject that with an illegal argument there. What were the corner cases with your linked lists? On insertion. Do you remember? Hopefully you're working on it for this week if you chose to do a linked list implementation. So what happens, say, when there's nothing in the tree? What happens when the tree is empty? So let's walk through this. Previous is going to be null. Current is going to be null, right? Because this root is empty. This while loop will never execute. We come down here and create a new child. New child that's set parent to null. That makes sense. Then we try to compare the element to the previous dot get element. What's going to happen right here? Remember, previous is null. So when I go null dot get element, is that going to work? It's going to throw a null pointer exception. So one corner case here. What happens when the tree is empty? If this dot root is equal to null, then we need to do something else. We of course need to create a new tree node, but it's not going to be a new child. What is it going to be? It's going to be the new root. The new root is equal to this new element, and we need to return true because we did have an effect on the tree. One thing that I've forgotten throughout this entire process, though, is keep track of the size, right? So if I'm about to return true, what should I do? This dot size plus plus, right? If I'm about to return true, because I just inserted a new leaf, I return true. Now over here in demo, right, I need a comparator first of all. I've got one over here in the tree utilities, where would I put it? My comparator for integers. There we go. And so I'll just pass that in. Tree utils dot comparator for integers, right? And system.out.println x. Let's make, now that I can test this really quick. Is 10 in there? No, false, right, because I have not put anything in there. So let's go ahead and insert a couple of things. Demo.insert 10. Right? Let's check that corner case, right? When we're adding a new element as the new root. Oh, it was able to find it. Right? Let's go ahead and insert a couple of other things. 20 and 15. There we go. Do we still find 10? Yeah. Are we getting lucky though, maybe? Right? Let's insert a whole bunch of things. Right? Insert 15. Well, here, let's insert a duplicate. Right? Right? All right, well, it didn't throw an exception. It didn't null out. It didn't crash. Maybe it's working. Right? Let's go ahead and insert a whole bunch of other things. Say 25, 5, 7, and 3. Right? I can call insert all day and it probably won't crash. But I certainly need to find these things. So let's go ahead and get rid of that. And am I able to find 3? Yeah, that worked too. All right. I have some pretty high confidence here that this is actually working. Is there another way that I could do this though? Don't I already have a tree here that is ready-made to check things? I do. In fact, I codified this over here in this function right here. Okay. It ends up inserting all of those things in the following order: 50, 40, 70, or 60, 20, 45, 90. Now, why did I go in that order? Let's look at the look at the tree over here. Why did I go 50, 40, 60, 20, 45, 90, 10, 24, 94, no, 49, 80, etc., etc. What kind of ordering was that, by the way? Where I'm going top to bottom, left to right. What order is that? Do you remember? BFS, breadth first search. Right? By inserting them in that order, I'm guaranteed to get this tree, or at least if all my code is correct, I should have this tree right here. Let's clean it up. Right. Okay. So let's go ahead and get this large BST. Right. It's certainly not a large binary search tree, but whatever. What is not compiling? Oh, not add, insert. There we go. There we go. And let's come over here to demo. And instead of this stuff, what I'll do is I'll call that function there tree utils dot. There we go. Now let's search for something that we know is in there. For example, we know that 45 is in there. There we go. 45. I found it. Right. Let's search for something else. I don't know, 12. That was the deepest in the tree. It's all the way down over here. Let's search for something that we get lucky on. 50. The root node, 50. Right. Let's search for something that we know is not in there. 76. Right. That ends up being null. That's a little bit more satisfying, right? That if I added stuff in this particular order, this BFS order, then I should get the topology of this tree. But do I have any assurances or guarantees that this is what the tree actually looks like right now? Right? Other than my word telling you that it is? No. So what I've done is I've actually created another function over here in my demo class, or my utility class. Right? What I've done is I've created a visualization function. Okay, to Tixie, and let's come. It's not compiling. Why? Okay, so yeah, it needs. I'm going to temporarily make this into a public variable, and then come back and fix that later. Right? To Tixie of this thing. So string s is equal to tree utils dot toTXE of my demo tree here. There we go. Right. And then system dot out dot println s. I'll explain what TXE here is in a second. Right. So if you've been using LaTeX for your design document throughout the semester, you might have had a question of how do I draw things? Of course, you can draw them using some sort of utility like draw.io or something like that and get it look a nice WYSIWYG, what you see is what you get kind of a way of doing it. Or you can go ahead and create this programmatically using LaTeX and a package called TXE. Right? Do I have a, I don't know, Overleaf? Overleaf.com? I think it's Overleaf, isn't it? Yeah. I don't want to sign up. Can I just get started? No, I don't want to explore features. Just get me started. Serious? I can't just do it? Templates? Academic journal? Can I just start? Come on. I can't just... Oh, here. Open as template? Fine. I will log in with my Google credentials. Yeah. All right, come on, I really don't want all this stuff. Fine. There's the abstract. These notes, there we go. I could probably put it here after the introduction. Come on, recompile. It's not going to let me. Darn it. Quick TXE render online. TXE maker? Maybe. Okay, no. Screw this. All right, so anyway, that TXE, if you put it into a LaTeX document, produces an image that looks like this. All right? In fact, I didn't draw this at all. I let TXE do it for me. Right? And in fact, I didn't write all of this code here to draw it. All I did was say, I want it to look something like this. Right? Where's my tree utils? I want it to look something like this. Just insert these things in this order and show me what you get. I just wanted a variety. I wanted some things, I wanted it deep enough that it mattered. I wanted some things with no left child. I wanted some things with no right child. And I wanted to make sure that there were some things with both children. And so I produced something that looked like this. Trust me that TXE will render something that looks like this. Right? But otherwise, as far as my binary tree is concerned, I can go back to private now. Right? I've got an insert method that probably works. I've got a search method that probably works. Right? Again, I don't have a 100% guarantee on it. I'd have to put this through its rigors through a JUnit test suite, like you'll be doing this Wednesday. Otherwise, what else do I need? Create, retrieve, update, and destroy. The destroy, right? I want to be able to public T delete or remove an element TK. There we go. Now, why did I not have a void function here? What I want to do is I want to do it like I did with my linked list. Removes and returns an element in this tree that matches the given key element. If no such element exists, returns null. There. So I need to remove an element. So what do you think that the first step here is? If you wanted to remove, say, 75, what do you got to do first? You got to find it. Right? So I see now a common theme. 3 times now, I've had to repeat, or I'm about to repeat, this basic code right here. Is there a better way of doing it? Yes. Right? That take this basic code here and put it into a private method that searches for a particular node with a particular key. Or failing that, gives you the previous value. Or does both. It finds the previous and the current and then gives them both back to you, if you can return 2 things. Right? There's no way to do that in Java cleanly. But in any case, I'm going to have to, 1, find the node. Right? 2, remove it. Uh-oh. How do I do that? Well, let's just figure it out, and then we'll save that for next time. If it's a leaf node, say 76, is there a problem with removing it? What do you do to a tree when you cut it? What is that action called? You're cutting the tree, you're trimming the tree, you are pruning it. So if this is a leaf, what can you do? Just sever it. How do you do it? Parent becomes null, sever that connection. Child becomes null, sever that connection, and you're done. Uh-oh. What if it's another value? What if it's, say, 60? What if it's, say, 20? What if it's 50 itself? Right? Can I do that? Can I leave a big giant gap here in my tree? Delete 50. Does that look like a tree to you anymore? Looks like 2 trees to me, and 2 trees become a forest. So I can't do that. Likewise, if I were to delete 60, could I do that? Maybe, right? But not generally. So we're going to have to figure this out next time. Right? If it's a leaf, pretty straightforward. If it's not a leaf, then it's not straightforward. We have to find something else. Okay? I'm going to find another solution. And we'll work on that next time.